Okay, guys, welcome. So today we're going to talk about the last part of, we're going to talk about the last part of the linear ODEs that we're going to look at. And that's the idea that if you are looking at a particular type of nonlinear ODE, but one that can be brought to a linear form by a certain transformation of variables, and that's known as what's called a Bernoulli equation. Right. So first, what we want to talk about is what does a Bernoulli equation look like? Well, it almost looks like a linear ODE, except on the right-hand side of the equation, we now have this nonlinear power of y. Right. So we now have y to some other power that, of course, would make this a nonlinear equation. Right. If you had y. If a was equal to 1, then it could have just been brought to the other side, and you have a homogeneous ODE. And if it's some other power of y, then, of course, it's nonlinear, right? So that's what we're going to talk about how we can deal with, right? So the sort of key to this is we're going to let u, by change of variables, we're going to let u be whatever our function y is to the 1 minus a power, right? So we're going to sort of go through the derivation for it. We'll talk about sort of what the general solution looks like, and then we'll do an example of that, okay? So first thing that we want to do is we differentiate u. Right, so this is just an application of the chain rule. So the 1 minus a comes out front. And then once you subtract 1 from that power, the 1 just disappears and you're left with minus a. And of course, by the chain rule, we need to multiply by this y prime. Now, of course, we know that y prime from the above equation, right, from this one. If we move the p times y to the other side, well, we know that y prime is just g times y to the a minus p times y. So we're going to make that substitution here. We're going to substitute this in for y prime, and that's where this is coming from. Now, if we clean this up and we multiply by through, for example, this y to the minus a and this y to the a will cancel. And the other one, we will get a what? So we'll get a 1 minus a power, right? So then once you simplify, that's what you're seeing in this equation here. Right, so once we multiply through by the y to the minus a, that's what we're going to be left with. And then, of course, we can use the fact that we made our original substitution on the basis from up here that u was equal to y to the 1 minus a. So we're going to plug this u in for this y to the 1 minus a. And then once you move some stuff around, you can eventually arrive at this equation, which of course is now linear, right? So this is now a linear ODE. Right. So now, given a specific type of nonlinear ODE, we now know a method that's going to allow us to convert this to something that is linear. And of course, that's something that we know how to solve, right? So let's look at an example. What we're going to do is we're going to solve the logistic equation, which on its own, of course, is nonlinear, right? Because you have that y squared term. Right, but of course, if you move the ay over, you have y prime minus ay is equal to minus by squared. And of course, that's a Bernoulli equation, right? So that's where this is coming from here, right? So of course, this is a Bernoulli equation, and now your 2 is like your a in this case, right? So a is equal to 2. And of course, since we make the substitution of u being equal to y to the 1 minus a, right? If a is 2, then we get that our u is equal to y to the negative 1, right? Or you can think of it as 1 over y if you like. But since we know that we're going to be differentiating u in the next step, it's going to be nicer to think of it as y to the negative 1, right? So now when we differentiate, again, u prime here is y to the -1. So when we take that derivative, negative comes out front, we drop the exponent by 1, we now got y to the, or sorry, we have negative y to the -2, and then of course by the chain rule we need this y prime. Okay, but again we know that y prime from the original equation is ay minus by squared. So that's what we're substituting in here. And then of course we can multiply through by our negative y to the -2. And then after some simplification, we get this. Right? And then of course we use the fact that since u was equal to y to the -1st, we can plug in our u into this equation. And now we end up with the linear ODE. Of course, once we write it in its usual standard form over here, we get the ODE of u prime plus a times u is equal to b. All right. Now, you can use the methods in the previous video that we talked about on non-homogeneous linear ODEs to solve this. And you can eventually show that the solution, and you should try to verify it on your own, you can show that the solution is given by this. Right. And of course, that's the general solution because we don't know an initial condition, at least in this case. So this is a general solution of the logistic equation. Well, the way that we've defined it right now, right? So again, the last thing that we need to do is our original equation was in terms of y, right? So we don't care about this, what it is in terms of u, we want to know what it is in terms of y. But this is a simple calculation to verify. Since u is equal to 1 over y, you can then show that y is equal to 1 over the reciprocal of what we originally found for u. Right. So this is, of course, probably if you've done some work with a logistic model before, this is probably how you've seen it presented. Right. So this is the logistic model in a non-differential equation setting here. Right. So I've just made a sort of a comment here that this is an important model in population dynamics because for the most part, so far, if you're not familiar with the logistic model, you'll know that one common model for presenting population dynamics is an exponential model. But of course, this is only valid for a certain amount of time, right? Because an exponential model is going to look something like this. And then, of course, it grows faster and faster without bound. Or if you want to look at a decreasing model, it decreases faster and faster without bound, right? But of course, this isn't feasible in long term because if you think about population dynamics on, say, a planet Earth, eventually you're going to have too many people and not enough resources, right? So there's sort of some limiting factors there that prevents this from growing without bound, and that's sort of what the logistic model aims to account for. So the logistic model version is going to look more something like this. So it's going to start out as an exponential model, but then after a while, you're going to sort of taper off and flatten out here, right? And you sort of have this threshold that you're never going to pass, right? And that threshold is usually referred to as the carrying capacity, right? So, or the maximum allowable population, right? So that's sort of the application behind the logistic model. But the main idea is that we can now take many nonlinear ODEs as long as they are in this certain form or can be brought to the certain form, and we can transform it into a linear ODE and solve it using methods that we've already discussed. Right. So that wraps up this video on Bernoulli equations, a little introduction to population dynamics. So hope you enjoyed, and I will see you next time.